Welcome to this video where we're going to take a look at logarithms and laws of logarithms. For A-level maths, of course, you'll need to know how to deal with logarithms. And here are some of the main properties of logarithms that you need to know for your A-level course. In the following, A is understood to be a positive number and usually greater than 1. Log to the base A of x equals y is equivalent to saying that x equals a to the power of y. A to the power of log to the base a of x equals x, which equals log to the base a of a to the power of x. Log to the base a of a equals 1, and log to the base a of 1 equals 0. Log to the base a of x plus log to the base a of y equals log to the base a of x times y. Log to the base a of x minus log to the base a of y equals log to the base a of x divided by y. Log to the base a of x to the power of y equals y times log to the base a of x. And log to the base a of b equals log to the base c of b divided by log to the base c of a, where c is any usually convenient positive number. This final rule is sometimes called the change of base rule, and a special case of the change of base rule is when c is chosen to be equal to b, which gives log to the base a of b equals 1 over log to the base b of a. In the rule that says log to the base a of x plus log to the base a of y equals log to the base a of x times y, notice that the base is the same for each of the logarithms involved. And similarly for the rule which says log to the base a of x minus log to the base a of y equals log to the base a of x divided by y. There's various different notations that you'll encounter when dealing with logarithms at A level. For example, log to the base a of x, log x on its own. A logarithm written without a base explicitly stated can either mean that the base is not important to take into consideration, but more usually this notation means that the base is 10. That is, usually we have log x without a base explicitly written is shorthand for log to the base 10 of x. ln x said the natural logarithm of x. Natural logarithms are logarithms whose base is e. That is, the natural logarithm of x is alternative notation for log to the base e of x. Logarithms to this base are very common, and arguably they're the most common logarithms that mathematicians encounter, which is why they kind of have their own notation. It's important to note that the expression log to the base a of x does not mean log to the base a multiplied by x. This is one of the many errors that people often make when dealing with logarithms, and another one is, for example, log to the base a of x plus log to the base a of y equals log to the base a of x plus y. This is not a law of logarithms, and it almost goes without saying that errors like this need to be avoided. There are, of course, many other errors that are made. The point is that the laws of logarithms need to be used very carefully. So what are logarithms and why do we need them? Logarithms are the inverse operation of exponentials, and this can be compared with, say, subtraction being the inverse operation of addition, or division being the inverse operation of multiplication. The law of logarithms stated previously, a to the power of logarithm to the base a of x equals log to the base a of a to the power of x, shows that exponential functions and logarithmic functions are inverse functions. Logarithms allow us to answer the question, which number x is such that a to the power of x equals b for two given numbers a and b? The answer, of course, is x equals log to the base a of b. And therefore, logarithms allow us to rearrange expressions of the form a to the power of x equals b. Addition, subtraction, multiplication, division, raising to a constant power and taking roots, no combination of these will enable us to rearrange this form of expression to make x the subject. And logarithms will need to be used in a variety of different contexts in order to solve problems. So let's take a look at some simple examples to start with. Number 1. Solve the equation 5 to the power of x equals 17 for x. Of course, the answer is x equals log to the base 5 of 17, which is obtained by directly applying the first rule that I stated at the start of this video. Log to the base a of x equals y is equivalent to saying that x equals a to the power of y. The expression log to the base 5 of 17 is an exact solution. If the answer is required to be given as a decimal, then grab your calculator to find the answer in a decimal form as something like 1.7603744428, etc. And you need to be clear whether your answer is to be given as an exact value, which usually means not in decimal form, or as a decimal. If a decimal form is required, then you need also to be clear about the degree of accuracy. For example, 2 significant figures, 3 decimal places, and so on. Question 2. Write the expression 2 log to the base a of x minus a half log to the base a of y plus 3 as a single logarithm. So using the rules of logarithms, we have that 2 times log to the base a of x equals log to the base a of x squared. A half log to the base a of y equals log to the base a of y to the power of a half, which can also be written as log to the base a of the square root of y. And 3 is equal to 3 times log to the base a of a, which of course is equal to log to the base a of a cubed. So the expression can be rewritten as log to the base a of x squared minus log to the base a of the square root of y plus log to the base a of a cubed. And so again, using the laws of logarithms, we have that this expression can be written as log to the base a of x squared times a cubed divided by the square root of y, which of course is written as a single logarithm. So we're done. Let's move on to some further examples, and in these examples I'll look at some more involved problems, and I'll also explain more carefully what I'm doing as I go through the problems. As I solve the problems, I'll explain, at least to the best of my ability, what kinds of things I notice, what kind of possible approaches and solutions may be going through my head, and so on. And I deliberately want to avoid giving the impression that there is a single way to approach things. There are often many different approaches that you can take. Find an expression for the exact value of x which solves the equation 5 to the power of 3x minus 1 equals 2 to the power of 3 minus 7x. So there's a couple of different ways that this equation can be solved. Possibly in an exam you would be given a specific form to aim for with your answer, which would potentially give some clues about the direction to go in initially. However, in this particular case, you're free to choose your preferred form. When dealing with logarithms, then I will tend to opt for natural logarithms. Pure mathematics rarely uses logarithms other than natural logarithms, and since using the properties of logarithms outlined at the start of this video, it can easily be shown using the change of base rule, for example, that any logarithm can be expressed in terms of any other logarithm. So to solve this equation, I'll start by taking natural logarithms of each side to give the natural logarithm of 5 to the power of 3x minus 1 equals the natural logarithm of 2 to the power of 3 minus 7x. And so, using the property that log to the base a of x to the power of k is equal to k times the logarithm to the base a of x, applied to each side we get 3x minus 1 times the natural logarithm of 5 is equal to 3 minus 7x times the natural logarithm of 2. Expanding this out gives 3x times the natural logarithm of 5 minus the natural logarithm of 5 is equal to 3 times the natural logarithm of 2 minus 7x times the natural logarithm of 2. And so x times the expression in the brackets is equal to 3 natural logarithm of 2 plus natural logarithm of 5, and therefore x is equal to the expression shown on the screen. And that's it. Of course, other possibilities would be x equals 3 log to the base 23 of 2 plus log to the base 23 of 5 divided by 3 log to the base 23 of 5 plus 7 log to the base 23 of 2. Why have I chosen 23 as the base here? Because I can. Or we could have x equals 3 plus log to the base 2 of 5 divided by 3 log to the base 2 of 5 plus 7. So here we can see that the base of the logarithms is 2, which effectively simplifies the expression to a certain extent. Of course, we could choose any positive number as the base. Of all the possible ways of expressing the answer to the question that we've just done, my personal preference here is, of course, the one that uses natural logarithms. I think it just looks prettier than all the others. Do you agree? Leave a comment in the comments section with your thoughts. Solve the equation 2 times log to the base 3 of x plus 12 log to the base x of 3 equals 11, where x is greater than 1. So here straight away, I'd notice that the bases of the logarithms are different. So there are many of the laws of logarithms which I'd maybe like to use, but which are unfortunately not directly applicable. However, what I do notice is that I have log to the base 3 of x and log to the base x of 3, which absolutely screams change of base to me, because I know that log to the base x of 3 is equal to 1 over log to the base 3 of x. So I could possibly replace the log to the base x of 3 in the equation with 1 over log to the base 3 of x. And of course, this is just an idea, and it may or may not work. When solving problems, I'm always prepared for an idea that I might have not to work. And if that's the case, then yes, it can be a bit frustrating, but then I just have to move on and try something else. And next time, in theory at least, I'll know better. So let's go with this idea, and we get 2 log to the base 3 of x plus 12 over log to the base 3 of x equals 11. So now I can clearly see where this is going, and I'm pretty sure that it's going to work. It's effectively going to be a disguised or hidden quadratic. So I'll multiply through my log to the base 3 of x to get 2 times log to the base 3 of x all squared plus 12 equals 11 log to the base 3 of x, giving 2 times log to the base 3 of x all squared minus 11 log to the base 3 of x plus 12 equals 0. And this factorizes into 2 log to the base 3 of x minus 3 times log to the base 3 of x minus 4 equals 0. And so we have log to the base 3 of x equals 3 halves, or log to the base 3 of x equals 4. And so finally, x is equal to 3 to the power of 3 halves, or even better, 3 times the square root of 3, or x equals 3 to the power of 4, which of course is equal to 81. And we're done. Easy peasy, lemon squeezy. As ever, answers in an exact form unless specifically told otherwise, and in this case, even though I have a preference for natural logarithms, which I've already mentioned, I didn't really see any point in replacing the logarithms to base 3 with natural logarithms. I think in this case it would just end up creating more work. Needless to say, it's important that you learn these laws of logarithms and are able to confidently apply them to solve problems. You'll often need to be able to recognize for yourself when the laws of logarithms are required. The confidence that you need will only really come through practice, solving a wide range of sufficiently challenging problems on a regular basis, and through attempting to solve problems, sometimes failing and sometimes succeeding. In the cases where you fail, then you need to try to find out where you've gone wrong. When learning about logarithms, I found it very helpful to experiment with the laws of logarithms a bit to see what kinds of things I could do with them. So some important points here to know and ideally understand are logarithms and exponentials are inverse operations. Understand laws of logarithms, and I'm going to be going into more detail with these shortly in this video. And you need to have experience working with logarithms in a variety of different contexts, both simple and more complicated contexts, both obvious and less obvious contexts. So now we come to the additional material section, the extra stuff. This section that we're coming into now is not required for A-level mathematics. This section is simply to give additional background material to provide some context for logarithms for anyone who's interested, and to look at logarithms in more detail to get a better understanding. This is the part of the video where we let our hair down and just go with the flow. This material will, I hope, answer some of your questions that you may have about logarithms, but also provoke further questions about logarithms or mathematics in general. I hope that this section encourages you to deepen your understanding of mathematics and possibly conduct your own independent research. I don't intend to make this section comprehensive and or self-contained. Very few, if any, parts of mathematics can be completely isolated. There may be questions that I leave either accidentally or deliberately unanswered, and you may have to find the answer to the question that you have through your own efforts by using the resources that you have available to you. Don't panic if you don't understand everything that I talk about in this section. If you do already understand everything, then you're probably already way beyond A-level and you don't really need to be watching this video, because some of the concepts that I talk about will go beyond the concepts that you will encounter at A-level. Nevertheless, I hope that you find something useful and interesting in this section. So let's have a look at some of the derivations of the laws of logarithms. Let's have a look at how some of the laws of logarithms that I gave at the beginning of this video might actually come about. So we start with the property a to the power of log to the base a of x equals log to the base a of a to the power of x, which establishes that logarithms and exponentials are inverse operations. And so it immediately follows from this that log to the base a of a is equal to log to the base a of a to the power of 1, which of course is equal to 1. But what about some of those other properties? So in particular, we know that for suitable values of a, x and y, that a to the power of log to the base a of x is equal to x, and a to the power of log to the base a of y is equal to y. Therefore, x times y is equal to a to the power of log to the base a of x times a to the power of log to the base a of y. But by using the laws of indices, we have that a to the power of log to the base a of x times a to the power of log to the base a of y is equal to a to the power of the sum of log to the base a of x and log to the base a of y. And therefore, x times y is equal to a to the power of the sum of log to the base a of x plus log to the base a of y. And so finally, log to the base a of x times y is equal to log to the base a of x plus log to the base a of y. And we also have, using laws of indices, that a to the power of k times log to the base a of x is equal to a to the power of log to the base a of x all to the power of k, which of course is equal to x to the power of k. And therefore, k times log to the base a of x is equal to log to the base a of x to the power of k. And therefore, to summarise the properties of logarithms that we've deduced so far, we have that a to the power of x equals b is equivalent to x equals log to the base a of b, a to the power of log to the base a of x equals x, log to the base a of x times y is equal to log to the base a of x plus log to the base a of y, and k times log to the base a of x equals log to the base a of x to the power of k. From this last point, it can easily be seen that log to the base a of 1 is equal to log to the base a of x to the power of 0, since x to the power of 0 is equal to 1, which equals 0 times log to the base a of x, which of course is equal to 0. That is, log to the base a of 1 is equal to 0. We also have the following: a to the power of log to the base a of b equals b. Then for any c greater than 0 and c not equal to 1, log to the base c of a to the power of log to the base a of b is equal to log to the base c of b. And so log to the base a of b times log to the base c of a is equal to log to the base c of b, giving log to the base a of b equals log to the base c of b divided by log to the base c of a. So as mentioned previously, this is called the change of base rule. This rule allows a logarithm to be written in terms of any other logarithm. The new base c can be chosen at your own convenience. And indeed, a special case of the change of base rule is the case when we choose c equals b, which gives, provided b is not equal to 1, log to the base a of b is equal to 1 over log to the base b of a. And thus we have, as some basic algebraic properties of logarithms, those properties shown on the screen now. So here we've started with exponential functions, where we've assumed all the usual properties of exponential functions, and then we derive logarithmic functions from them. I won't explain how exponential functions can be suitably defined for all real values here though. I may include this in a different video. However, we can also start from the other direction. We can start by defining a function and show that this function has all the properties as indicated in the laws of logarithms. Then we can define a new function called an exponential function from this, and then we can go on to show that this new exponential function has all the usual properties that we expect an exponential function to have. So here we effectively start with logarithms and arrive at a suitable concept of exponentials. So let's pretend for the moment that we're starting from a position of not having a defined notion of logarithm. We can define a function as shown on the screen now. ln x is equal to the integral from 1 to x of 1 over t with respect to t when x is greater than or equal to 1, and ln x is equal to minus the integral from x to 1 of 1 over t with respect to t for 0 less than or x is less than 1. And we might suggestively call this the natural logarithm function. It can be shown, but I'll not include the details here, that this function has all the properties of logarithms that we expect it to have. Moreover, we can also show that the inverse function of this function is a function which satisfies all of the properties that we associate with exponential functions, and so the inverse function of this natural logarithm function is the exponential function. General logarithms and exponentials can be derived from the natural logarithm function with some adaptations. So now, going in a different direction, Leonhard Euler, in his famous work Introductio in Analysin Infinitorum, Introduction to the Analysis of Infinities, explains that logarithmic functions are transcendental, meaning that the logarithms of rational and algebraic irrational numbers will be transcendental numbers. Chapter 6 of Euler's introduction is titled De Quantitatibus Exponentialibus ac Logarithmis, on exponential and logarithmic quantities, and this chapter is concerned with developing the notions of exponentials and logarithms and their properties. In section 104 in particular of this chapter, Euler establishes some of the laws of logarithms that I've introduced in this video. On the screen now is the text of section 104 from Euler's original work in Latin on the left, along with my attempted translation of it on the right. And Euler goes on to show in section 105 of chapter 6 that logarithmic functions are transcendental functions. I've uploaded some videos on my other YouTube channel, the Second Number Class, which looks at Euler's work in more detail, with one of these videos, part 3, looking at the contents of chapter 6 in particular. I'll include a link to these videos in the description to this video. Modern pure mathematics is usually interested in representing the exact numbers corresponding to logarithms rather than decimal approximations, and so pure mathematics understands an expression such as log to the base 2 of 5 as being a symbol which stands for a specific number, in exactly the same way that the numeral 2 is a symbol for a specific number, or the symbol the square root of 10 is a symbol for a specific number. However, mathematicians in previous centuries have often needed decimal representations of numbers, and in particular logarithms. Logarithm tables could be used, along with a lot of faffing around, to obtain reasonably good decimal approximations to logarithms. Even though there are an infinite number of possible bases for logarithms, it was only necessary to have logarithm tables for one base, which was often base 10, and such logarithms were called common logarithms, and then, using the laws of logarithms given in this video, logarithms to other bases could be computed. To find the number whose common logarithm is, say, 2.3064735001, we split the number up into the characteristic, which is equal to the greatest integer smaller than the logarithm, and the mantissa, which is the string of digits after the decimal point. In this case, the characteristic is equal to 2, and the mantissa is 306473501. Using the mantissa, we can use logarithm tables to tell us some of the digits of the number whose common logarithm this is, and the characteristic will tell us where to place the decimal point in the string of digits. So, using logarithm tables, and I've put a link in the description to this video to the logarithm tables that I'm using, the mantissa of the logarithm that I'm interested in is 306473501, and this corresponds to the number n. From the tables, I can find the mantissa 30643 corresponds to the number with digits 2025, and I find the mantissa 30664 corresponds to the number with digits 2026. So an increase in 1 in the number from 2025 to 2026 corresponds to an increase in 21 in the mantissa. The increase of the mantissa 30643 to 30647, that's the first 5 digits of the mantissa corresponding to n, is an increase of 4, which is approximately 1/5 of the increase from 30643 to 30664, and so I put a 2 on the end of 2025. Think of it as almost like adding 0.2 to give 20252. And since the characteristic is 2, Then I place the decimal point after the third digit from the left to give 202.52. And therefore n is approximately equal to 202.52. And this is only to get the common logarithm, that is to base 10. If I wanted to know to another base, then I'd have even more work to do. So I told you there was a lot of faffing around. Also, there's another problem. If I want to find a number whose logarithm is, say, minus 1.47389, because 47389 is not the correct manticity to use here, it's common to write a negative number which represents a logarithm such as minus 1.47389 as minus 1.47389 equals 8.52611 minus 10, where 52611 is the correct manticity to use, and the minus 10 reminds me that it's actually minus 1.47389 that I'm working with, and thus the characteristic is minus 2. It's a completely separate question entirely how the logarithms which we find in the logarithm tables were originally calculated, and I'm not going to go there in this video. So I think that's enough for this video. I hope you found it useful and interesting. If there's anything that you'd like to ask about anything in this video, or about A-level maths in general, then please feel free to drop me an email or leave a comment in the comments section. Please remember to subscribe and hit the like button to show your support. More videos will be added to this channel over the coming weeks and months. Thank you for watching, and I'll look forward to uploading the next video for you.